We have an illustrious panel today. I'm very proud that one of our biggest webinars ever, and one of our biggest panel ever. We have first of all, ladies first. Mary Beaton, Queen of Bolts, as a late entrant, and I'm afraid we haven't updated all of the entry slides here. But Mary has contributed greatly to this webinar, supporting Sud with some of his magnificent slides. Sud is, of course, here presenting today. Specialist consultant, lifetime knowledge in our industry, and has come up with the suggestion for today's webinar and prepared it today with Mary. Tony Smith, of course, a world-renowned inventor of the PAPI, is here and will be on the panel to answer your questions later. Carl Johnson, I thought you were on holiday today, Carl.
I am, but I'm here for the holiday.
So Carl is here for you. So I mean, thank you, Carl, for that. Much appreciated. Keith, of course, and condolences for you that don't know. I just should let you know that Keith lost his wife recently, and so condolences from us all, Keith, and thank you for joining us. And I thought.
Thank you, guys. Thank you.
Yeah. Thank you. And Nick, of course, is with us today from first time. He's joining us as he's Tailor Made Systems Managing Director for MARMS in East Africa, where he's made a very successful start in bringing safety and compliance to that region of the world. I, of course, am Managing Director of Tailor Made Systems and TMS Training Solutions, and not least Felicity Parks and Damon Creed are here, or also as our team that actually do all the hard work in preparing for today's webinar, setting everything up for you, and looking after all of our interests generally. So thank you all to the team. And without any further ado, I'd like to kick off now. Stuart Ford will now introduce the fundamentals of airport lighting series circuit as part of our Meggering Day.
Thank you, Robert. Thank you. Good to be with you all. And I'm so thankful for Robert's initiation, getting all this going here back a few years ago, and the opportunity to have to share opinions, share viewpoints, and go through some of the basics of our industry and what we're supposed to be specialists in. So we're going to talk about the installation measurements today of cable insulation, measurement of cable insulation, and but first of all, we're going to talk about a little bit about fundamentals of the airport lighting circuit, which overshadows most everything that we do talk about. And we're talking about the series circuit. The first indication I had of series circuit uses is when they used to use them on street lighting circuits over here in the States, and they needed a circuit with numerous lights on it over a long distance, over several miles in some instances, and they wanted all those lights to be the same intensity. They probably were not, for some of the reasons that we're going to talk about today, and they didn't have the photometric test equipment and so forth to handle those things back in those early 1900s. And but then also we graduated to airports, and we started putting series circuits around the boundary, the barrier, the boundary of airports. And by doing that, we were telling the pilot, don't go beyond this point. And then we did floodlighting for the pastures that many of them were, where planes would land. So anyways, we're past that. We're in the modern day now, and we got constant current regulators. And the fundamentals of the series circuit that are there and we must remember and be considerate of is, and I've listed some here. We have to remember, this is basic. Current will leave the CCR, that constant current regulator, flow through the circuit components, and then return to the CCR. Once the current leaves the CCR, it's looking for the best way back to the CCR. And we're trying to make sure that it goes back on the cable that we've put out there to supply power to the lights and not taking some shortcut route through the ground. Same current should flow through all components in the lighting circuit. Otherwise, how are we going to get the same brightness out of the fixtures if we don't have the same current flowing through each of those lighting fixtures? And that's a thing that we're very concerned with today on our circuits. Make sure that the output meets the requirements of the standards, and all the lights in a particular system are equally performing. The current will take every available path back to its source, with the majority of current flowing in the path of least resistance. So once the current leaves the regulator there, it's going to follow the conductor if that looks like the best source or best path back to the power source. It'll follow that, but it's along the route somewhere. If it comes across something, hey, this looks like a better path, a little less resistance. Let's go this route. Well, if that happens, we don't want that. We want to keep it on the path of the current of the conductor so that we get the proper illumination out of our lighting fixtures. And to do that, we need the current conductor should have an adequate surrounding barrier of insulation, which prevents the current from finding an undesirable path. And we just mentioned that. The more pressure of voltage applied to push the current along, the more likely the current will penetrate the insulation barrier and find an undesirable path. And we'll get just a little bit more in that in the next slide or two. And we'll move ahead now. So the principles of insulation resistant testing, which we commonly call Meggering. And here's the history of the word. A megger, or sometimes megar, in some sources, is often used as a colloquial term for an insulation tester, a circuit tester which puts a very high voltage at a very low current across two conductors to make sure they are properly insulated. The word is short for meggometer. Megger is the registered trademark of Megger Group Limited, who have manufactured insulation testers since 1889, and they're located over in the UK. The Megger applies a DC voltage between the 2 points, and the current flow between those 2 points depends on the resistance of the material between the 2 points. And so that's what we're measuring, the resistance between the 2 points. And we use Ohm's law, which is the most common law I think we ever come in contact in the electrical industry. Ohm's law, the current equals the voltage over the resistance. I equals current, E equals voltage, R equals ohm. And here's a little cartoon characters we put in here to kind of indicate what we're talking about and make it a little bit humorous of Ohm's law. You see, we have Mr. Ampere there. He's trying to get through this conductor, but there's a resistance point there applied by Mr. Ohm. And he's there got a lasso around the conductor, and he's trying to tighten it down so Mr. Amp can't get through. But along comes Mr. Volt, and he gets stronger and stronger. And the more voltage we give him, the more strength we give him, the more likely he is to be able to get the amp through that resistive point in the circuit. And so that's what he's doing. That's an indication of what is happening in the circuits that we're dealing with. On we go. Principles of Meggering. Now we're going to get into the principles that we're going to be considering as we talk this morning. And I'm going to ask, like Carl is on, Keith is on, Robert is on, and anybody that has any particular comments, feel free to jump in. We just can't jump in too much or we won't finish in our design time. It says it is theoretically possible to raise the voltage to such a high enough level that an insulation material, earth and so forth, will break down and allow current to find a path through the insulation material. This would be analogous to increasing the water pressure.
Do you need to get a drink there?
Yeah,
So
when I get to the bottom right here, I will. This I get talking too loud. I get too excited. And point B here, this would be analogous to increasing the water pressure in a PVC pipe to such a high PSI that small leaks start to occur in the pipe, which may also involve a blowout or major rupture of the pipe. In our next slide, we'll show an example of that happening. And there it is. I took this picture of the a hose in front of my house out there, and I noticed, my goodness, look, it's got little puncture holes in it, and water is leaking out of there. And why is that? It's because the pressure in that hose is strong enough to break through the leakage points in that hose, and the water comes out. So in this case, the nozzle was off. The PSI from the water pressure in the house, which is pretty good here, was forcing water to escape through these weak points in the conductor, in the insulation of the hose. So the higher the voltage on a conductor to ground, the more current leakage will occur. Here's an example using the hose and water and pressure to illustrate that point. On we go. Okay, further principles. The current, we measure circuits.
Sorry about that. Go on.
Yeah, that's okay. I'm used to jumping around. We measure circuits to determine if over time there has been any reduction in the insulation or resistance capability of the airport lighting cables. Is that insulation changing over time? And that is what we have, that's our responsibility, is to get out and measure the circuits at dedicated times and to gather a history of what is happening. And we base many of our decisions and our actions on the trend that we see developing as we measure the circuits over time on a specific schedule. A reduction in the installation capability of an airport lighting circuit cable in multiple locations leads to increased current leakage to ground, which we are aware of, causing some lamps to have a reduction in lamp current and increasing the possibility of a circuit failure. We can have several leakage points to ground where those low resistant points to ground are such that the current is more attracted to leave the conductor at that point and go to another place on that cable where it finds it less resistive, and it jumps back on the conductor at that point. So what happens in the middle? The lights in the middle are dimmed or they're out in some instances. And so it's important that we don't have these multiple grounding or low resistant points to ground on the cable. And we always say, well, if you got one, you're okay. But if you got two, and then you got a problem. And that's the case. But we don't even want to get one developing, because we know if there's one, there's soon going to be two. So we move ahead. The current from a megger, and most of you probably have used meggers or seen meggers. If you're not, this is your challenge to start using meggers. The current from a megger is limited to just a few milliamps, 3 to 5 milliamps, low current, to prevent insulation breakdown. Lower cable insulation values will sometimes result in a lower than selected test voltage being applied in order to calculate insulation resistance within the restraints of available current. In other words, we've only got 3 to 5 milliamps that we need, and we're using 1,000 volts, let's say, to measure the cable. Well, it could be that we have so much leakage on that cable that all the 3 to 5 milliamps is going out, and the voltage then drops down because it is not able to do its job. And so in that case, we're not able to get a particular megger reading for that particular voltage on that particular cable. When the megger first applies voltage to the circuit, there is a higher inrush current until the capacitive effect of the conductor to ground is charged. The dielectric, the covering, the insulation covering on the conductor, depending on what shape it's in, it will build up a voltage there on the inrush current, and it has a capacitive effect on the conductor. How quick that happens depends on the quality of the cable insulation that we're testing. And then here is overview on insulation resistant testing. We're going to go into a lot of details on today, and but here is a document, and if you don't copy that down now. You can get it later on when the video is available again for review. But on that document written by another a co-instructor over here in the States, David Rainey, he talks about some of the various aspects of testing cable. What happens? How does a cable deteriorate? What are the paths of deterioration? And the other issue that we're going to talk about a little bit more is that what is the correct voltage for measuring a circuit? Can we measure a circuit with too high a voltage, which then causes further destruction of the cable installation or further paths of the installation to develop? And so what is the right voltage that we should be testing? We may test them with a high voltage when we first get the cables, or we may even high pot the cable by itself. But when we get them in the ground and the system is operating, what's the proper voltage that we should be measuring with? We'll have some discussion about that as we move along here. Simple diagram showing a typical measuring principle. We have the megger up there. That megger is, in this case, I've said the output voltage is 1,000 volts DC. And the megger will put a maximum of 5 milliamps. I said just previously that the maximum current out of a megger today is typically 3 to 5 milliamps. So we'll say it's giving 5 milliamps at 1,000 volts. Well, it comes out into this conductor, and if the conductor is such that it's leaking at points along that cable, along that conductor, and it's going to leak out, and it's going to look to go back to the source of its voltage. It's like the CCR, the current, once it leaks out, is looking for the best path back to the CCR. With the megger here, it's looking, once it escapes the conductor through the insulation, it's looking for the best path back to its source, which is the megger. And we have strategically placed out in the field a ground probe with a megger connected to that, and that's the negative terminal of the megger. And so that current, once it comes out from the cable, is going to gravitate and go through there, and we can measure that current. We measure the current, and then we can determine what the resistance is of that ground that current is traveling through. That's the general principle that we use. Put a voltage on the conductor, a high voltage on the conductor. In this case, it's 1,000 volts, and then we have a ground out in the ground, out in the area, out in the ground, which then measures what current comes out of that conductor and makes its way back to the ground. And we measure that, and we can determine what the resistance of that circuit is. Moving on. Now, our goal in our measuring here, what is our goal? Our goal is to measure the change in resistance between the conductor and path to the megger. In order to observe this change and develop an accurate history, we must. That's the key. There are variables when we do megger testing. The ground may have a different resistance one day than it does at another because of moisture content. But if we take readings at the most appropriate time and over a regular schedule, we then can look at all those readings, and from that we can see a trend developing. Even though we have changes each day, which could be due to the ground resistance changing, if we get trend over a period of time, we're going to get an indication what is happening to the resistance, or the resistance and from the cable. We're going to get an indication of what the insulation is on the cable and if it's deteriorating or not. That's what we're looking for as we look for a trend over time as we do all these particular readings. Okay, moving on. That's the question I asked just a few minutes ago. What is the most appropriate DC voltage for Meggering an airport lighting series circuit? I'm going to get some input on this from maybe Keith or Carl or anybody, but the voltage rating of the cable, is that key, or the normal operating voltage of the circuit? My position would be that after the circuit's installed and operating, then we would typically do a Megger reading using a voltage of probably 1,000 volts. We have 5,000 volt cable, but especially in the newer circuits, we have very few places on that circuit where there's ever even close to 5,000 volts. So if we use 1,000 volts, that's more conducive to the voltages we see there, and so we can keep an accurate record of what's happening with regard to the realm of the voltage that the circuit is operating. And so now there's some instances where initially you test for higher voltage. Keith, do you want to mention a little bit there?
Yeah. What there's different viewpoints all over the globe, really, in this. And whilst the standards, in accordance with the ICAO Zero Drone Design Manual Part 5, they state quite clearly that based upon the 1 microamp, 2 microamp rule associated with cable and the isolating transformers, then we can calculate what the minimum acceptable insulation resistance values are, but it's based upon 5,000 volts. So, using Ohm's law, as you mentioned earlier, we can calculate what the minimum acceptable insulation resistance values is. But you are quite right. We go from a 2.5 kVA CCR up to a 30 kVA CCR in the international marketplace. So clearly, then if you've got a 30 kVA, the voltage that you're going to if it's fully loaded, that's going to be what, 4,545, nearly, just below 5,000 volts. If it's a 2.5 kVA CCR, it's going to be dramatically lower. Plus, over time, why stress the circuit? Because once we put something in the field, then its life expectancy starts to reduce depending on where it is. And so, therefore, to stress that cable at 5,000 volts in accordance with the Aviation Design Manual is pretty stupid, I would suggest, So to use something like 1,000 volts and then monitor, and I know you're going to, talk about that, Seward, whether it's an automated monitoring system or whether you just monitor and keep records, etc. So to me, I think from a maintenance viewpoint, and let's face it, are we looking at it from an installation and a compliance viewpoint, or are we looking at it from a maintenance viewpoint? So from a maintenance viewpoint, the 1,000 volts, I think, would be a sensible, voltage to use for Meggering, and I think that's what you've adopted, certainly in the US under the FAA rules.
Yeah, that's right, Keith. I think that's sort of where we stabilized around 1,000 volts, is being accurate, but keeping the history is so important, and then seeing the trend develop. And you say, we don't hardly see any 30 kW regulators going in anymore, or 50 kWs. We used to have 50 kWs, they're fairly standard, 30 kWs. Now you're lucky if you see a 20 kW in some of the new circuits based on LEDs being used. And in case you didn't realize that LEDs are the light source of the future, and pretty soon we're going to be talking about circuits that really light only LEDs. Do we really need what we have today? And that gets me off on another subject, and I want to start that. But we also have automatic Meggering systems here that many manufacturers also offer them. They're integrated with the CCR and the control system you have, and the system is programmed to run a mugger test at a specific time with a selected voltage for a selective test duration. That helps to provide the most consistent ground resistance over time, and that's what we're looking for, history. So Some people run them very, very often. Others who maybe run them once a week, once a 2 weeks, whatever. But it always runs the test with the same parameters, so that when we average the results after a period of time, we will be able to find a trend developing, and that's what we're looking for, is a trend developing. And one other thing I was going to bring up when we were talking about cables just a minute ago here, and Keith was talking about that, that paper that I attached here, it talks about that some contractors, and I don't know how much often it's done, but some contractors, or airports, if you store cable, you want to make sure the ends are covered so you don't get any water, any dampness in getting into the cable in the installation. You want to make sure that's sealed. And sometimes the contractors, they do a high pot test on cable before they install it, just to make sure it meets the voltage requirements of the cable. Just a couple of other mentions of other options that are out there. Let's move on. Well, here's the World War II Megger, and Keith said that's the first one he ever used. And the voltage you get is how fast you can crank it. So that might come back on the market today for those that need exercise, arm exercise. Maybe that'll come back, and you can do your exercises as well as measure your circuit, but don't count on it. But this is one of the earlier World War II meggers. And the person that gave me this, it was the tester issued to my grandfather. And you still have one of those in your back pocket, Keith, once in a while that you can.
No, I'm afraid it went a long time ago.
Yeah, it's gone. It's gone. Well, then let's move on to another one. The next slide would show us this is more common 1,000-volt DC battery powered megger. And this is the one that a lot of you at the airport should have. And if you don't have it, you should have it. And this will allow you to put 1,000 volts DC out on the segment of the circuit or the whole circuit. And, you know, we can, when we think we have a problem in a particular area of the circuit, we can isolate that area, measure that circuit, that part of the circuit, and see what our reading is. And then we might measure the adjacent segment next to it and find that it's normal in our estimation. So we can isolate and find out where a problem is by doing just measuring particular circuit segments, or we measure the whole circuit, which is quite often the case that we do. So moving on to one more megger here that we got, and here's the one that will go up to 5,000 volt. 5,000 volt, and in that attachment that I listed back a few slides that David Rainey wrote, he did some testing on that. And just one example that he did was that he was measuring with 1,000 volts. He was measuring, I think it was 33 megohms on a circuit. Well, then he tested it with 5,000. That was with a 1,000 volt megger. Now with the 5,000 volt megger, the 33 megohms dropped down to like 13 megohms, because new paths were created for current to leave the conductor in the insulation by the additional voltage. Then when he went back to measure the megger reading again at 1,000 volts, which he had been using, the megger reading stayed the same at the 13 megohms. And so the damage had been done with the high voltage. So that's something we got to bear in mind, as Keith has just talked to us a little bit about a few seconds ago. So let's move on. Preventative maintenance. Well, here's principles of measuring. This is just a simple graphic for you, just so that you don't understand what's happening. And it was many years before we even talked about measuring circuits. I've been in the industry practically all my life. We never talked much about measuring circuits, and I guess maybe the airports did to some extent. But generally, you just operated your lights until they went out, and then you did your troubleshooting. Today, we don't have that luxury. We need to keep them operating in order to maintain the schedules that we have at our facility. But here's the principles. We have the megger DC volts put on the conductor, anywhere between 1,000 or 500 volts. And as I said, the automatic measuring, when it first came out, was 500 volts. But I think now that's higher than that on a lot of the automatic measuring systems. But so here we're saying 1,000 to 5,000 volt DC test voltage. You put it on the conductor, you see how much leakage you're going to have out of that insulation, that conductor insulation, and ever how much you got is going to flow through the ground back to the megger, and you're going to be able to read the resistance of that circuit. How many megohms of resistance do we have? If I do it today, it'll be maybe different tomorrow since I've had heavy rain during the night. So things change, and that's again why we keep accurate records and look for trends. We know that there's trends and variations in the ground, but there shouldn't be rapid changes in the insulation of the conductor. They would be more gradual, typically. And so that's what we're looking forward in checking, and that's okay. Next slide. So what we want to do is make regular checks. We want to make regular checks, set a time schedule, put a graph, put a chart on the wall that says when you're going to measure next and where you're going to measure and what are all the rules are for measuring. And then you want to do it at a specific time and keep the same time interval. Unless you have some major issue, keep the same time interval and see what the trend develops. And then, of course, all this is good if you don't keep accurate records, then you'll have no history to look back at to see what was it like a year ago today. It was much different, much higher. Notice the trend in the last 12 months, steadily downwards. Something is going to happen here in the future. And
One of
course,
Stuart,
yeah.
we had a question on this point. How regular should the checks be? How frequently should you do your mega testing?
Well, my answer to that would be that you know your airport based on testing you've done, and you maybe have to figure that out. I mean, if it's automatic testing, you can test it on a regular basis, on a daily basis, if you want to. But if you're going out there with your meter, you might want to do it on a monthly basis. So what do you think, Carl? And what do you think, Keith, on that number?
I think it's Keith here. I think a monthly basis to keep regular checks and keeping a record is pretty adequate.
Okay.
I would agree with Keith. If you live in an area like Florida where you have frequent thunderstorms, maybe after a storm, do a quick one to see if anything has been degraded. But otherwise, monthly checks for your trending would be a good way of doing it.
Yeah, I agree. Yep.
Certainly we see, because we do this with our CMMS. We see the trends are very important, but it's seasonal trends. So you need to winter wet weather in winter and dry weather in summer, and you'll see the patterns emerging. And if you can do them regularly, and keep a record of the weather conditions at the same time, the ground conditions, that's very useful.
But also, of course, geographical location makes a difference as well. For that very reason, Robert?
Yes.
Excellent comments. So that's the next point we had here. Be consistent in how the tests are conducted. You can't compare the previous test with this test if you're not consistent in the methods you use to do the tests. And then establish and record test points at various locations in each circuit where troubleshooting can be performed. And you can have points in your circuit out there where you have access to the circuit. It may be in a transformer housing, a base steel can housing, where you can get in there and you can isolate the circuit or a segment of the circuit, and you can test that segment of the circuit to see what's happening with regard to the meggering there, and you'll see a trend developing. Or if you know you have a problem there, you go to that point and you check it, and you find it's much lower megger reading than the adjacent segment of circuit. So it's all in keeping records. It's all in doing things on a regular basis. So important to do that. Go ahead to the next one there. So the time resistance method, I'm going to mention this just briefly, and I don't know if anybody, and I haven't really had any comments from anybody if they ever use it or not, but it's an independent way of judging the fairly independent of outside factors such as temperature or circuit size. And it can give conclusive information without records of past tests. This is a quick man's test, I think you would say, and if you don't have all the history, but by far you're better off having the history and looking at trending. But based on the absorption effect of good insulation compared to that of moist or contaminated insulation, you get different readings. Measure the difference between readings taken at a specific time intervals. Specific time intervals. Again, we have that important point. If insulation contains moisture or contaminants, a high leakage current will be present, keeping the resistance reading low. Now, if we look to the next slide, we'll see here that there's a graph. There's a graph there that was made up on a particular circuit, taking readings at particular points at different times. And you notice the insulation probably okay line there is that the Megger reading is continuing up during this 10-minute period on this test. But notice the other one is going down, is starting to trend down. That indicates that we've got some weak points in our insulation, and it may be moisture and dirt in there that is helping to make a path for that current to break through the insulation. And so that's another test you could do if you wanted to try that and see what difference the different readings were. Moving ahead, here's the 1 megohm rule. The 1 megohm rule that we often follow is for voltage ratings of less than 1,000 volts, the minimum resistance to ground should be 1 megohm. That's less than 1,000 volts on the circuit. That's a small circuit. It's maybe an LED circuit with a lot of lights today. Could be a fair number of lights, but it's only a 10 kW regulator, and or even less than that. But it says for voltage ratings of less than 1,000 volts, put on that particular circuit, the minimum resistance to ground should be 1 megohm. And then for voltage ratings greater than 1,000 volts, the minimum should be 1 megohm per 1,000 volts, which gets us to the point that a 5,000 volt airport lighting circuit equals 5 megohms minimum. If you had 5,000 volts on that circuit, and we don't really ever today hardly ever see 5,000 volts. So the 5 megohms is what, if on your 5 kV cable, we'll say it shouldn't be any less than that. If it's lower voltage on the cable, you can accept lower readings, but anything lower than 5 megohms, and if it's trending downward, it's time to start thinking about it. Okay, moving ahead. Here's a little graphic work that Mary performed for me, made up for me, just to give us a little better indication what we might see up there. And here's we've got a basic series circuit, and we've got it's a taxiway circuit, and the lights are all lit here. And we show a close-up of the circuit down below. You'll notice that down below there, it's got a connector that's apart, but we're going to ignore that just for the second because we're saying the circuit is operating. So moving on, we come to we're going to separate these out here, and we're going to see where that point is that the current is able to get out. It's out there, and show Mr. Amperage up there on the screen. He's the next slide, Mr. Amperage. He's standing there. He says, "Ha-ha, I've got a way out." Now the question is, where do I go? And I've got multiple options where I can go. I got to go where the least resistant path is, the fastest connection, fastest way back to the regulator. That's what it's going to be looking for. And if we're lucky enough to only have one point like this on the circuit, we're not going to know the difference. And we often say, if you got one low resistance point to ground, then you don't notice the difference out there. But when you get a second one, then that's where problems start coming. And here we'll say we have a current leakage due to cable installation cut or deterioration at this point here. And you notice, you see the lights all from that breakage point, from that cable problem, all the way across are out, or at least they're dim. And that's because the voltage, the current has found another path. So give me that path there, Robert. Hit that next one. And so, well, that was a little fast. There we go. But there's a path that's developed that comes out, and we made it slow motion, and so that we'll get up to the conductor again, and when it joins the conductor, the rest of the circuit acts normal. And so it just bypasses that part of the circuit. Kind of rare, but when you got a real low resistance to ground, it will happen. Now let's go on to the next example. And this is, it's the same thing, leakage to ground due to connector kits. And again, I could go for hours, I think. That's a little exaggeration talking about connector kit installation, but if they're done properly, we shouldn't have this happening. Now just click that thing once, and we'll see. There we go. The path is gone, the same path. It's gone up to the same point on the circuit to complete the path. And we got those lights out there that are going to be extinguished, or they're going to be dim. Let's move on to the next one. Okay, here we've got a case. We got a case where there's two options available. And let's hit the next one here, the next slide. And we see we're coming back up to the conductor here in a different location. And so the lights that are on either side of where the current is leaving and where it's entering the conductor as the lights are on. But the center section is out because there's another path there for us. And let's go to the next one. And the next one is going to show us that we could have a dual path. And I don't see that coming up here, but what we show there, that's going back. We have the same path. And then we also, typically on the slide, we show that there's a current flowing through the conductor still also. The conductor is, so the current is split between going through the conductor and taking the bypass. So Mr. Amp, when he comes out there, said, which route's the best? Well, I don't know. I might as well stay on the road that we've been on instead of taking this other road, which looks pretty attractive, but I'll stay on the main copper conductor. And so that's what happens. And so you have still dim lights out there, you may, at times. Let's hit that once more there, Robert. Okay. All right, there we've got it. Let's move on. Let's move on. Well, there's the one I was looking for here, which has the split current. You see the conductor's got the orange reddish color showing it's still conducting current from the initial leakage point to where it goes back onto the conductor along the circuit. So we got the path there, plus we got a path that's going through the ground. So we got a split path. We could have multiple paths like that on an airport, multiple paths, if we've got old conditions, old cable, poor insulation. And that's when it comes really, you really got a job in finding out where the problem is. And it may be you need a whole new cable installation. Depends on the years. Well, here's a little bit of a summary here that only qualified persons should perform the installation resistance test. You got to know what you're doing. You got to verify the circuit is de-energized. The test procedure you use must be repeatable. How often you're ever going to do it, you want to make sure you do it the same way every time. And all circuits should measure at least 500 megohms. That's kind of a rule we put in there. And if Carl or Keith have any, I know the military over in the UK, I think Keith said that they've got to have at least that. You might comment on that briefly, Keith.
Yeah, there is a standard. There's a question that's come up in the Q&A. There is a standard in the ICAO's Aerodrome Design Manual Part 5, which refers to a 1 microamp allowable earth leakage, because the nature of where our equipment is. 1 microamp leakage for each 100 meters of primary cable, and 2 microamps leakage to earth for each transformer in the circuit. So obviously each circuit has different number of transformers and different lengths. So you calculate per circuit. Calculated that using Ohm's law at the 5,000 volt design criteria, gives you the minimum acceptable insulation resistance for that particular circuit. Then you decide what you're going to do from a maintenance viewpoint when you're going to look for the possible fault in the fault diagnosis technique. And so basically, a rule of thumb is that when you're, depending whether it's a wet location or a dry location, at 2 times the calculated value, or 5 times a calculated value, you may want to decide 10 times a calculated value when you start to look for that fault. And that fault, it's mend it before it breaks, basically.
Okay, thanks, Keith. And the next statement here is get to know your circuits and establish your own standards. And there's a lot to this. You know your airport. You have a history of what's happened. You have a history of when things are going bad from previous experiences. So you get to know, and what are your limits? What are your limits? We know what is suggested. We're saying generally 1,000 volt Megger tests is adequate and for finding, but you want to maintain that same voltage check all the time because you're looking for a trend. And the leakages developed today in a test may have been magnified the next time you do the test. And so you're looking at a trend with the same, keeping everything else, all the parameters the same, except for the fact that all the parameters are the same, except you must do it on a regular basis. And be proactive and make regular measurements. We've said that. Keep good records. That's so important. And last of all, believe what the instruments are telling you. You go out there and look at your instrument and say, it can't be this bad. Well, believe the instrument until you prove otherwise the instrument is correct. Moving on. It's this equivalent circuit of a good cable. And we're not going to spend much time on that. That shows a counterpoise. That's another subject for another future time. Grounding. That shows the counterpoise grounded to the steel can with a lug on the outside. Very common over here in the States for all our in-pavement lights to have a ground lug on the outside and they're connected to the counterpoise and so forth. So we'll, that's just a kind of an overall view that we could use as a basis for some future discussions. All righty. Here's another one, and Carl brought this up, and I think it's a good one. It's the infinity indication. If you're out there working on the circuits and you're measuring and you're trying to meg the circuits, and the infinity indication is a delight to the repair technician, because he says it's beyond my reach, it's infinity, but represents a void to the diagnostician, the person who's trying to diagnose what is actually going on in that circuit doesn't want to hear the word it's an infinity indication or it's beyond what we can, it's beyond, there's no indication. We got infinity, megging is beautiful, it's the top of the line. Well, then we go down, infinity is not a measurement. It is an indication that the insulation being tested has an insulation resistance value that exceeds the measuring capabilities of the test equipment. You say it's an infinity reading. It's got an infinite Megger capability, but that's only true for the instrument that you're using. If you were using a different tester, maybe a different voltage, that wouldn't be true. So you've got to at least state on that report, it should be recorded as greater than 1,000 megohms or highest available range on the test equipment. What is your test equipment limit, top limit for Meggering circuits? If it's above that, state it's above 1,000 megohms. If it's 500 megohms, state it's above 500 megohms. We need that piece of information because we got to know when we start getting back into the areas that we can measure again. We got to go timing on that and when we did it. Questions on that, comments?
Sure, that information came from a Biddle Megger manual. There's a lot of good information you can get from their website as well.
Yeah, that's good. And again, that document that I attached earlier, I gave you the link for earlier, get that at some point and read that document. I thought it was very well written by David. Okay, moving on. Here we are. Effects of temperature. Temperature and resistance are inversely proportional. Do you live in the Middle East or do you live in Antarctica? You know, and that has an effect on the readings that you're going to be getting. And the general rule of thumb here is for every 10 degrees C increase in temperature, the resistance is half. The resistance drops in half of that particular item that we're measuring, or segment of circuit, etc. For every 10 degrees C decrease in temperature, that the resistance doubles. The resistance doubles from what it was. So those are two general rules. And depending on if you're in an area where you get a lot of extremes in high and low temperatures, these also are a factor. And so actually you keeping a record of the temperature when you did your test would be of value. If you have a 20 below zero today and next week, 3 weeks from now, it's Fahrenheit I'm speaking of, 70 degrees above zero or 80 degrees. There's a difference in temperature. So take that, record the temperature, and factor that into your observation that you make on your airport. Again, a lot of this is how you configure the information, how you do it, and how you think, hopefully following the standards, that your meggering should be. How good should your meggering read? And we've given you guidelines here today as to what it should be. But it's your airport, and you better make sure you meet the standards that are dictated to you either by the FAA, ICAO, or whatever you're dealing with. But when it comes right down to it, our airport has some unique properties that other airports don't have, and we have to judge our results by knowing those particular properties of our airport. Thank you. Next. Here's a practical application. It shows some devices here, and we're measuring the resistance, the meggering, we're measuring them, and the insulation resistance over a long period of time. You know, we got out to 6 years, and here, and we notice, for example, the top one is trending down. And, you know, what's the time life on our circuit? What is it? I've heard this morning, I think maybe 15, 20 years is a typical lifetime of a circuit. And maybe it's more than that. It depends on where you are, what your environment is. But it's nice to have a record so that it gives you an indication of what's going on over time. You leave this record on the wall for your replacements. If somebody comes in and takes your job, that's something they can look at and know this is what it was 3 years ago today. So that's important. Comments? Moving on.
So part of this would be, we'll drop back one slide. Part of this is trend analysis as well. If you look strictly at the absolute values, apparatus A has a better value than apparatus B. But if you look at the curves with a downward trend of apparatus A, even though it has an initial higher absolute value, it's probably going to fail first. So you'd want to spend more attention or spend more time figuring out what's wrong with apparatus A than you would at apparatus B by looking at the trends.
And that's the reason every time we measure our systems, we're going to keep a record so we can look at those trends. All right, I think that's the last slide we have there. We got time for questions and discussion. And Robert, you take it away for a while? Or anybody put the questions in? I don't have the questions in front of me. And any of us can get involved in answering.
Good, thank you.
What I've been doing is answering the questions as you've been talking, Sir. You know, that are coming up, and you know, the general questions, you know, is they talk, you know, questions associated with what's the minimum acceptable value of IR before we start to do fault finding and maintenance? What is the voltage we should use for new circuits, you know, in installation and commissioning phase, you know, for projects, and or during maintenance? Those kind of questions are coming up. And I think they're really really valid questions, because generally speaking, in an AGL circuit of today, the equipment actually is highly reliable. The weak point is us, the people putting the connectors on. You know, whether it's installation or maintenance. Because let's face it, when you're changing a connector, you're not in a workshop on a bench. We're out in the field, hung over a can or a transformer pit. Hot, cold. We're not the most efficient people as human beings when we're in that scenario. So this connector becomes the weak point in the overall circuit, doesn't it?
Correct. One thing I wanted to just add that I didn't say, and when we have automatic measuring systems, that we can adjust the voltages on that to what we want to measure, but it gives us an instantaneous reading. It gives us an alarm in most of the systems that I'm familiar with. If you have a 10 kW loss in your circuit, or a 5% loss or a 10% loss in your circuit load, it gives you an alarm. And if that happens, you know there's been an immediate issue. There's been two shorts to ground develop, or something has happened in which requires immediate. So that trend is a sudden trend. It's a 10% loss in VA on that circuit, and you ought to get right out there and check it out. Okay, sorry.
CCRs, you know, in accordance with the IEC technical standard on the international market, do not have that built in to the requirement. It's only really on, you know, under the FAA, and so, but it's a really good indication, isn't it? Eh? You know, if you've got a short two earths, one earth's on a circuit, no operational effect. Two earths on a circuit, and operational effect. And that operational effect means that that we, you know, the load has gone down, therefore the voltage goes down. Simple as that, eh?
Good. Robert, you're
Right. Sorry. One of the from a photometric testing point of view, one of the, you know, traditionally the main thing we used to see was on interleaved circuits. You could readily pick with photometric testing. You can readily identify circuits that are underperforming and address them as part of a commissioning procedure, because these underperformances are not often visible to the human eye. So that's one thing. But now with the introduction of LED circuits, particularly where you're putting LEDs on an older CCR, that you can have significant underperformance by the nature of the resistance being so low for the LED circuit, such that it manifests itself. I've seen on PAPIs, the LED PAPIs massively underperforming, but nobody noticing at the airfield because they're still very bright. So there's one thing to watch out for in particular there. And that's where measurement, you can't manage what you don't measure. And then, of course, the other circumstances on runway circuits, you can often manifest itself in flickering lights as the CCR is trying to fight with trying to fight to hold a stable current. So these
that becomes because of the not so much with the IGBT, the low harmonic regulators, but with thyristor regulators, that's more prominent, and because of the nature of the waveform that from a thyristor-based CCR of it, whereby so that and that only happens when you either it's step 1 or step 2 concept. When you're at the higher value of current, which is the maximum intensity, that tends not to occur,
So what are the steps to avoid this? A lot of our airports, a lot of our participants here are in the process of upgrading from incandescent to LED light sources for their visual aids. How can they mitigate the issues associated with CCR LED incompatibility?
Well, most and the things that we have found is that the first step is, we're going to change to LED technology, but they still retain the thyristor-based CCRs. But the thing is, with the thyristor-based CCRs, you tap the output of the CCR main transformer according to the load. That means the number of lights, etc. You've got out in the field. So if you're changing from an incandescent light, a tungsten halogen to an LED, you're going to be dropping, 2/3 of your load demand, electrical load demand. So you have to tap down your CCR outputs, and many airports do not do that. That is one of the issues that occurs.
And that will occur also if you're in an airport where you're changing from incandescent to LED, and if you leave the same transformer in there, you're putting a 5-watt light in place of a 30 or 40-watt lamp, you'll notice that will also affect the loading on the regulator. And actually, you're loading the regulator too much. You should actually drop the transformer down to a 10-15 watt transformer if you're using LED lights. And so that's another issue that comes on the scene.
Yeah, correct.
Yeah. Can I say something triggered a bit by something Robert said a few minutes ago about LEDs still looking bright, but not having the output. With an incandescent lamp, of course, if your current goes down, then the color changes. And most people actually, common understanding of lights, they're brighter because, or less bright because of the color they are. So if you've got a lighting system and you start to lose performance, the color changes. And that's what most people calibrate as being reduction in output. That's their measure, the color changes. Now with LEDs, of course, you're in a different world. So you can still have the same color, but have a lower output significantly. And I think that's partly the reason why those LEDs, LED pappies, people were not picking up the fact that the light output was down because the color isn't changing.
Very good point, Tony. Very good point.
Yeah, that's a good point. Another thing to notice, we think about the LED fixture versus the incandescent fixture. If you drop the current coming to an incandescent fixture, I'm just off the top of my head, or you drop it by 10%. You go from, if it's a 6.6 amp circuit, you go down to 6.6 amps or thereabout. The light output is going to drop off at least 50%.
Yeah.
Now, when you're in the LED circuit, they can take minor changes. It's more of a direct relationship. It's more direct than the indirect that you have with incandescent. And if you're off a little bit of amperage on your, of course, each LED fixture has its own power supply, depending on the tolerance of that. But typically a small change in the incandescent current will not magnify itself in as great a change in light output as it would in an incandescent.
Yeah.
Yeah, well, sorry to interrupt, but just one more. I think one of the major installation malpractices is when you are merging circuits. For example, if you have an existing circuit and you are mixing an halogen, probably with the introduction of remotes, and then you have situations where some transformers are open and others are probably with open lamps in some circuits. This also leads to a lot of disruptions or bonking of the CCR. So these are the pre-installation prerequisites checks that needs to be completed before the circuit is commissioned. So in instances where you commission these circuits, before these checks are thoroughly inspected and supervised, then obviously it leads to some of these experiences we have in many airports with the lack of proper oversight.
Thank you there, Nick.
Thank you.
There's Nick, Keith is answering some of the questions there. If you want to address those questions to the panel, Keith, so that we can all share them. I think one of them concerned the use of the shielded versus of course, in the United States, primarily they use unshielded cable, and in the rest of the world use shielded cable, most cases.
The case here is that you measure just exactly the same way, you know, where, you know, there is no difference in the way you're measuring. But of course, what does occur is that it's when it comes to the earthing network, and Seward has already said, you know, that the consistency of the ground, is it a wet ground, is it a dry ground, are we on rock, etc., are we on sand? Now, where you actually get your earth for your mega, it can affect things. So it's a subject which we can't answer in this short space of time. What I'm saying, eh? Mm-hmm. There's a lot of variance associated with that answer, depending on where you are.
Yeah, that's right. There's another one which was closely linked to that in determination of the age and the longevity of series isolation transformers. But I think there are so many factors that could be involved, especially in an AGL circuit, if it's the type of the cable you're using, the environmental factors, or the loading capacity. So depending on the type of cables you use, for example, typically the XPLE normally lasts longer than the PVCs. And if you look at the transformers for those who are in the Middle East or in the extreme regions, so the variations in the operating temperatures or the loading conditions and obviously the quality from the manufacturers, this will determine on how these assets will serve you in your airfield.
Thank you, Nick. Yes. There's a question from Rajesh, well, a statement from Rajesh says ADM Part 5 2017 provides required IR values for maintenance for different circuit lengths. Keith, we were talking about this earlier, on whether to apply temperature degrading factor, 50% decrease with 10 degrees centigrade over the minimum resistance values. This is certainly, we're talking about minimum acceptable insulation resistance, measuring according to the length of cables or the number of transformers. Perhaps you could share that point with us.
Well, the new issue of the Aerodrome Design Manual Part 4 has kind of added comments associated with this. I am personally not in favor of all those comments. The generality of it is good, but I find that depending on who is reading it, the way it's been written, you can interpret things somewhat differently. Maybe that's the diplomatic way of saying it.
Yes, that certainly is the case, and we've come across that, haven't we, Tony, in
Yes.
relation to Pappy ILS sighting,
Indeed, yes.
and we are addressing that directly with the Visualize Working Group. So
Yes,
That's-
well, we're
that's-
trying to.
trying to, yes. And can the yeah, and I think the answer, I think we know the answer. So the an anonymous attendee, I just asked, points out, the fluctuation of the current measured by the CCR can be the result of a faulty circuit. I think it can be a number of reasons, as well as not just stepping down the CCR. So good. Well, look, thank you everybody for your participation today. It's now 3:10. I think it's been an excellent topic, Seward. Thank you for suggesting it, and thank you, Carl. Thank you, Mary, and thank you everybody for your participation in today's webinar. If you do have any more questions, please fire them at us. The video of the recording of the webinar will be posted on the website, on our website, for you to watch at your leisure, to catch up on any points you may have missed, or and I know certainly in some parts of the world where the time difference is huge, actually use them for meetings. So greetings to you guys in I think GHD in Australia, I think particularly for that. I know. So so thank you very much, everyone. Thank you to Damon and Felicity for setting everything up for us today so well. And the next webinar will be held at the MARMS AGL workshop. It will be a live webinar with an audience. So we're very excited by this departure into virtually television. But we hope to bring you a very interesting subject matter built around the workshop agenda. So we're covering topics such as competence, compliance, regulatory updates, and what's new in the airfield lighting world. So we've got a very interesting and varied content there with audience participation. So very much look forward to seeing you on the 27th of February. It will be 2 p.m. UK time. No, I'm being corrected there. It'll be 15:30 UK time. So we'll send out notice in advance. So it'll be a slightly different time. We're very much looking forward to seeing you all there for our new adventure into live audience participation webinars. And I'll see you in a month's time. And good luck with everything you're doing, and stay safe. Thank you. Goodbye.
Thank you.
Here's our